This video is going to illustrate how to use graphs to set up the component selections process. A preliminary design problem is an inverse problem, and has for objective to determine component characteristics that will answer performances requirements. To solve this problem, we will use sizing processes, calculus sequences, or optimization algorithms when it is not possible to fully inverse the equation we possess. It is in our interest to have the minimal design variables to make the optimization algorithm process easier. The optimization problem's definition depends on the form of the sizing process. We will now see how to use these graphs to set up sizing process. Knowledge required to design a mechatronic system is divided into two layers. First, a system layer, which represents all the interactions between components that allows to evaluate the global performances of our system. It uses 0D 1D models in algebraic or simulation environments. Then, a component layer, which represents knowledges of several sizing jobs. This layer uses finite elements or sizing codes models that are specific to each sizing job. Each of these layers can be represented by algebraic equations, such as scaling laws, or obtained if necessary thanks to regression on response surfaces. We generally have one set of equations that we must put in order to have a sizing code. The first step we advise here is to graphically represent these equations in a bipartite double graph. A first step links the system layer equations to global system parameters and to component parameters. These equations usually represent the different sizing scenarios of our system. It is the mechatronic layer. A second one links the components' characteristics between themselves thanks to estimation models such as scaling laws. At this level, links are not oriented yet. The objective is now to give an orientation to these links so that we obtain the sizing process. The best case would be to obtain a succession of calculus without any algebraic loop, without any unknown variables, and without any useless input variables. The process to reach this case is explained as followed. First, represent the equations in a graphic way as shown before. Then, give an orientation to the equations. And finally, break the algebraic loops if necessary. After representing the several equations, you must give an orientation to these equations by making sure the problem is neither under constraint nor over constraint. You will probably have to set some variables as known or to be defined as constraints for some quantities. Once the problem is well balanced, which means there are as many unknown variables as equations, you'll have to verify the succession of calculus does not contain any algebraic loop. You can delete these loops by manipulating the equations and adding constraints on the optimization algorithm. At the end of this process, the optimization problem is well defined. This first problem is going to illustrate a problem you might encounter under constraint equations. This example represents equations of a servo valve hydraulic jack system. Some variables that directly come from the specifications can be considered as known as inputs, so performances that are non-negotiables, objectives to reach, the specifications requiring to be as good as possible, or constraints, which means limits you must not overcome. On these graphs, a rectangle represents a quantity defined as an input, an hexagon as an output that is useful to evaluate a constraint or an objective. A double line indicates a quantity evaluated by an equation, the output, which means all the rest is considered as an input. These equations 3 and 5 are under a constraint. It is therefore necessary to set some quantities, here P0 and dP known, as known, if you want to determine S and Q num. Two new inputs appear in this case. We decided to choose these quantities as inputs because they're easy to fix from the technology we know or easy to approximate and to bound. dP num is generally equal to 70 bars in the servo valve catalogs, and the pressure 0 is limited to a value between 0 and P net, the network pressure. A second type of problem can be encountered, over constraint equations. While we select roller screws, the choice can be determined by static and dynamic limits criteria. One quantity can be influenced by two equations, here F0. One solution consists in transferring an equation in the solver constraints. For instance, the dynamic load equation 2. We have to respect this equation, so we add an oversizing coefficient in the equation 1. If F0 is not sufficient to have a roll screw that can bear the dynamic load, the solver will augment Kc so that we respect the dynamic load constraint. In a short way, we modified the over constraint problem in an optimization issue with one more constraint and one more input variable, Kc. We must say Kc is bound with 1 as a minimum. The last typical problem is the existence of an algebraic loop. Here, the choice of a motor, based on its max torque, depends on its own inertia, which means we have to know what a motor to choose before choosing it. This algebraic loop can be broken by admitting that the inertia torque is meaningless to evaluate the max torque, which allows us to choose a motor. The global torque with the inertia can subsequently be evaluated and compared to the torque of the motor we selected. To respect this last constraint, we add an oversizing constraint to the first sizing process. The solver will choose by itself the value of this oversizing coefficient, which is at least 1 in the case of negligible inertia effects.